Welcome back, students. Today we will learn differentiation of the vector fields. Already we have learned in last class about vector fields, scalar fields, and differentiation of the scalar field, that is gradient. In this class we are going to cover these topics: divergence, curl, second order differentiation of the fields. Divergence is, as it sounds, how much field or its flux is coming out of the point of interest. Let me say this is the point of interest, then how much field is coming out or flux. That quantity we are going to define it later. Then curl is something how a field is rotating near a point of interest. Let us formally define divergence in Cartesian coordinates. It can be defined in other coordinate systems also, but right now we are interested only in Cartesian coordinate system, that is XYZ. This is the region of space in which we have defined vector field. Any vector field can be expressed using components. This is the vector field here, as it is shown here. It has x component, then it has a component in y direction, fy, component in z direction. Then divergence is denoted like this: r, using del operator I can write this as divergence as shown here, and it is defined by take the x partial derivative of the x component only, then similarly y component only, then z component of the field with respect to z, then you add all these three derivatives. Observe here no ijk's have come, only numbers. Therefore ultimately you will get just a number at any point or scalar at any point, no direction. Therefore, after taking divergence of a vector field, you will have a scalar field. Now, to give a geometrical interpretation or meaning, I have to define something called flux. Let us say I want to calculate at this point divergence. Then electric field is coming out of this small patch ds. You can define a vector which is normal to this small patch of the surface. Then you take field defined somewhere in this region and take dot product. That f dot ds is called as small flux through this small area. Total flux, if you want to define for a bigger surface like this is a cube which has 6 surfaces. Now if you want to define total flux coming out of this side surfaces, then you have to do this, uh, you have to take integration. Total flux will be defined by integration over the closed surface. Now, geometrical meaning of the divergence. Divergence at any point represents total flux coming out of the surface of a cube. It can be any shape, not only cube, any closed surface. But let us stick to cube. Divergence at any point represents total flux coming out of the surface of a cube of very small volume. Why small? Because I am interested only in this point, how field is varying. Therefore, if we take larger or bigger cubes, then it takes account of the vector set very far away points. But I am interested only in small region around this point. It is defined in calculus sense, then you make that cube volume go to 0. Okay, in that sense we have to calculate the divergence. Once again I will repeat, divergence at any point represents total flux coming out of surface of a cube of very small volume. This is the geometrical meaning. Now intuitively let us grasp using our intuition. What is the divergence at this point? You ask this question and we will see here it is coming out. If you say here also it is coming out, therefore something it should be coming out of this small surface, small cube. Therefore, you should have all the partial derivatives greater than 0. Hence, our divergence of the vector field here, it must be greater than 0 or positive. Here, everything is coming in field. Therefore, if you consider at this point, all the derivatives are negative. Therefore, divergence is negative here. In fluid dynamics, these are called sink, these are called sources. Here, what comes in, that is leaving also. Therefore, no variation in the field. Hence, all the derivatives are 0. Therefore, divergence is 0. Next, we will define solenoidal field. It's also an important concept. A vector field has zero divergence at all points in a region. Then we say it is a solenoidal field. If you consider this is the region of the space, then there are field defined. Field is not zero at every point, but if you calculate divergence at any point in this region, then that will be 0. Div of f is 0 at all these regions. Then we will say that field is solenoidal in this region. A good example is magnetic field. Since we know that divergence of B is 0 at all points. This is the second Maxwell equation. Later you will learn. Therefore, magnetic field is always solenoidal. Let us practice practice this concept of divergence with few numerical problems. So, suppose uh, I want to calculate field, divergence of the field. Field is given by field is given by f is equal to 3x I plus 4y j plus 9 zk. Then divergence of f is given by dou fx by dou x plus dou by dou y of fy plus dou fz divided by dou z, and you will have fx. Here fx is 3x, x component 3x, therefore after differentiation you will get 3 from this, and similarly 4 from this, and here 9z, therefore you will get 9, therefore 13, that will become 16, and since 16 is greater than 0, that is at every point divergence is positive. Divergence is positive. We will have another problem. Calculate the divergence of field f is equal to 3 times position vector r. That field at every point, it is nothing but 3 times the position vector. Calculate its divergence. Divergence of f is dou. This vector can be written also, it can be written as 3 times xi plus 3 times yj plus 3 times zk. Therefore, dou fx by dou x, dou fy by dou y, dou z by dou z is equal to, and this number here 3x, therefore 3 plus 3 plus 3 is 9. Another some interesting example where it varies with respect to point. Divergence also varies with point to point. Let us consider f is equal to 3x square plus 2y plus 9z cube. All the we will have, since it is a vector field, we must have ijk's. Okay, div f is equal to derivative of this x component, that will be 6x, derivative of this y component 2y, that will be 2, derivative of this 9z cube, that will be 27z square. Now as x and y point varies, x and y z also vary, therefore divergence f is also a function of point, therefore it is a scalar field. If you want to calculate this divergence at any particular point, say at point x is equal to 1, y is equal to 0, z is equal to 2, then div f at this point will become 6 plus 2, 27 into 4, that is 116.